So, warm welcome to the 20th lecture on the subject of digital signal processing and its applications. We have been discussing the synthesis of discrete time filters, and we should recapitulate for a couple of minutes what we have done so far on that theme. We have been looking at the ideal filter first, the ideal discrete time filters. And we realized that they are unrealizable, they are disqualified, so to speak, on many counts, on 3 counts to be more specific. We then moved on to putting down a realistic set of specifications. Okay. And in the realistic set of specifications, the pass band and the stop band have a tolerance. And there is a transition band. These are the 2 things that need to be taken care of. Now, given that you have allowed for a non-zero tolerance in the pass band and the stop band, or pass bands and stop bands as the case may be, and that you have allowed a transition band, the resultant specifications are always realizable. We noted that. So, with these compromises, the discrete filter is realizable. Now, in fact, the good thing is it is realizable both as IIR and FIR. That is, you could realize it by using a finite impulse response system or an infinite impulse response system. You have the choice between the 2. Now, obviously, the finite impulse response system has several advantages to its credit. We shall see them, but even right now we can see that the finite impulse response system is stable unconditionally. Even in the presence of numerical errors, it would be stable. That is not the case for infinite impulse response system. They could become unstable. Moreover, we shall see later that it is only the finite impulse response system that can give us the phase response that we desire. The phase is unavoidable. We noticed that last time. We said the specifications are on the magnitude, not on the phase. The phase is a necessary evil. It normally follows as a consequence of the magnitude response that we are trying to meet. Right? But there again, the FIR filter scores over the IIR filter. We will see that later. Now, in all these circumstances, why at all do we choose the IIR filter for design then? And we noted that. We noted why that was the case. We said that, in spite of all this, the IIR filter can offer advantages in the amount of computation, the complexity of the system, or the computational or the hardware software resource demand, and therefore we still consider the possibility of IIR systems. And there is another reason: IIR systems can be designed by taking inspiration from analog systems. So, there is a history of analog filter design of which we can take advantage. We can take advantage of the methods available for analog filter design and use a universal process to convert from analog to discrete time, and that is a huge advantage in the design of IIR filters. So, for all these reasons, we agreed that we would begin with IIR filter design. We decided to begin with IIR filter design. And the basic philosophy that we would follow in IIR filter design is to employ known methods from analog IIR filter design. In fact, we also made a remark, we noted last time that when we consider analog filters, we have no choice. There is no finite, there is no non-trivial finite impulse response analog filter. In fact, that is one of the reasons why we go to discrete time. So, there is no finite impulse response. Analog filter. And therefore, it is only by IIR filter design that we can take advantage of the knowledge of analog filter design, right. Now, after you design the analog filter, what do you do next? The analog filter is subjected to what we call an S to Z transformation. Essentially, we said that the analog filter is described in terms of the Laplace variable. So, we looked at the system function of the analog filter, which would essentially be a function of the Laplace variable S. We are also given an interpretation to the Laplace variable the last time. We noted that the Laplace variable is essentially representative of the derivative operation. And we could spend just a minute on justifying that again. Actually, the Laplace transform is an effort to express any function in terms of e raised to the power of ST's, complex exponentials. And it is quite clear that the derivative of e raised to the power of ST is S times e raised to the power of ST. So, multiplication by S is like a derivative operator on e raised to the power of ST. And if you think of any function as comprised of several e raised to the power of ST's, then multiplication by S individually on each of these e raised to the power of ST's amounts to taking a derivative. So, in that sense, multiplication by S or the operator S or the variable S is representative of a derivative. Now, we note this because this is what will inspire us to come up with an S to Z transformation. In contrast, the variable Z or the complex variable Z in the discrete domain relates to shift, to movement. When we multiply a Z transform by Z inverse, we are shifting the sequence by one step forward, and when we multiply it by Z, we are shifting it by one step backwards. So, Z corresponds to shift. Is that right? Let us make a note of that. Z in the discrete domain corresponds to shift. So, what we need is an approximation of derivatives in terms of shifts in terms of, in fact, a linear combination of shifts. The better we can make the linear, the better we can approximate a derivative in terms of shifts, the better we will do in going from analog to discrete time by replacing S by, of course, a rational function of Z. Now, we had also put down certain criteria on that rational function of Z. In fact, the S to Z transform should do the following: preserve rationality. that means the transform should be rational on its own. You see, because an analog filter system function is expected to be rational. Rationality corresponds to realizability even in the analog domain. So, the analog system function itself is expected to be rational. Now, you want to retain that rationality when you go into the discrete domain by making an S to Z transformation. So, the only way you can do it is if you replace S by a rational function of Z. So, that transformation must be rational. Secondly, the transformation must preserve stability. And now we want to interpret what preservation of stability means. Preservation of stability means a proper mapping from different parts of the S plane to different parts of the Z plane. In fact, let us now put down specifics there. So, you see, what does it mean? It means in the S plane, let's mark the regions of importance in the S plane and the Z plane. So, you have the Z plane here and you have the S plane there. The contours of importance are the unit circle in the Z plane or mod Z equal to 1 and the imaginary axis in the S plane S equal to j omega. We had seen that S equal to j omega corresponds to sinusoids. So, the imaginary axis and the unit circle must be a mapping one on the other. That is a requirement. Of course, that is actually not a requirement by itself, it is nothing to do with stability. It is a requirement that when you have a frequency response already constructed in the analog domain, it moves to a corresponding frequency response in the discrete domain. But what is important for stability is that the left half of the S plane go into the interior of the unit circle and the right half of the S plane go to the exterior of the unit circle. This is what is important for stability. Now, if this happens, if the right half of the S plane maps into the exterior of the unit circle and if the left half of the S plane maps to the interior of the unit circle and of course, the imaginary axis maps to the unit circle, then we will very easily be able to show that one cannot result in, it cannot happen that we design a stable analog filter and it becomes an unstable discrete time filter. We can show that without too much of difficulty. In fact, let us prove that. So, what we are saying is S equal to j omega must map into mod Z equal to 1. Real part of S greater than 0 must map to mod Z greater than 1 and real part of S less than 0, that is the left half plane, must map to mod Z less than 1. This is the right half. Now, remember what we are saying is we are making a transformation on S. S is the independent variable in the system function in the analog domain. Suppose it could happen that you have Now you see, remember, we are retaining, now again, we have assumed the filter to be causal. So, let us also, I think we should make a note of that, we should emphasize that. What we are saying is that we take a causal analog filter and use this S to Z, whatever this transformation be. We will have to now come to that transformation, but we must know what we want out of that transformation. So, a causal analog filter must move into a causal discrete time filter or discrete filter. Now, if the discrete filter is causal, we know what to expect from its poles. We are assuming the discrete filter is causal, we want it to be rational because it should be realizable, and we have a causal rational discrete time system. We know what to expect of its poles. If it is to be stable, the poles must lie inside the unit circle, they have no choice. Suppose a pole happened to go outside the unit circle. Now, what is a pole? A pole is the point where that system function diverges, goes to infinity, and that must have come from some point in S. Under the transformation, some point in S must have brought you to that point in Z. Now, a point on the, if the point in Z happens to be outside the unit circle, it could have only come from a point on the right half plane in S. It could not have come from a point in the left half plane of S, if we have ensured that there is a closed relationship of left half plane to interior of the unit circle, imaginary axis to unit circle, and right half plane to the exterior of the unit circle. If you have ensured that there is this disjoint relationship, then you cannot have a pole on the exterior of the unit circle, because that should have come then from a point in the right half plane. It could not have come from a point in the left half plane. But you cannot have a pole in the original system in the right half plane because it is stable. Of course, that filter has to be stable. So, if we ensure that this is satisfied, that left half goes to interior, imaginary axis goes to the unit circle, and right half goes to the exterior, we are guaranteed that a stable analog filter will go into a stable discrete time filter. Is that clear to everybody? Yes. So, that is of course, but you see, we have of course, now as a consequence of that, because left half goes to interior, right half goes to exterior, naturally the unit circle and the imaginary axis will have a one-to-one relationship. However, we do not want any arbitrary relationship there too. We had made a remark on that too. We said that relationship must also be monotonically increasing. The relationship, so this is the condition number, we had already given two conditions so far. The third condition is that there is a monotonically increasing sinusoidal frequency relationship, increasing one-to-one sinusoidal frequency relationship. Between omega and small omega. This is the analog sinusoidal frequency and this is the discrete sinusoidal frequency, normalized of course. Small omega is the normalized discrete frequency. Now, why does it need to be one-to-one? We have also put down the explanation. It needs to be one-to-one because we want to keep the nature of the filter intact. One-to-one and increasing to retain the nature of the filter. You see, for example, in the analog domain, if you happen to have a low pass filter, with its pass band and stop band edges, as we talked about the last time, and tolerances and transition bands, then under this transformation, 0 must come to 0 As we move from 0 towards infinity, we must go from 0 to pi. Therefore, infinity must be in 1 to 1 with pi. As we go from 0 to minus infinity, we should be moving from 0 to minus pi, and therefore, minus infinity should be 1 to 1 with minus pi. And because of the increasing nature, we are going to have the same pattern translated, albeit with a nonlinear distortion. It has to be nonlinear. There is no option. But the nature of the filter is retained. So, we noted that this transformation has no choice but to be nonlinear. The transformation between capital omega and small omega, or the analog sinusoidal frequency and the normalized discrete angular frequency. It has no choice but to be nonlinear. So, all these are the conditions that this transformation must satisfy. And now we need to use our intuition and our insights to construct such a transformation. We also have a hint from where to begin. The transformation must essentially be an approximation of the derivative operator in terms of shifts. And what simpler example of a derivative approximation can we have than to subtract the current or the past sample from the current sample. You see, what is a derivative? A derivative is essentially a rate of change, and the smallest unit of time on which we can measure change in this discrete system is one sample time. So, if we look at the change in one sample time, we have an approximation to the derivative. So, we are tempted to consider the following candidate for this transformation. We are tempted to consider S equal to 1 minus Z inverse. What it means is, we are approximating the derivative by taking the difference between the current sample and the past sample. Now, we do not need to go too far to see that this is not adequate as far as our conditions go. In fact, all that we need to do is to write Z in terms of S. So, Z inverse is clearly 1 minus S, and therefore, Z is 1 by 1 minus S, if we take this transformation to be true. And then we only need to substitute S equal to j omega. And then we have 1 by 1 minus j omega does not even have a magnitude of 1. So, mod of 1 by 1 minus j omega is not 1 for all omega. So, we have failed on a very important count anyway. And in fact, this transformation, we should have, if this is Z, then the imaginary axis should have gone to the unit circle. So, we are failing on that count anyway. And anyway, this is not going to be, so a simple approximation like this is not going to help us. In fact, let us use some more cues to lead us to a transformation of choice. Let us do it the other way. Let us put Z equal to e raised to the power j omega in the same transformation and see what we get. We get 1 minus e raised to the power minus j omega, and that can be rewritten as e raised to the power minus j omega by 2 times 2j sin omega. So, there are two counts on which, of course, we were pessimistic a minute ago, and we noted that the transformation was not all right, but then, to move to a solution, you can't remain pessimistic. You have to find some way out of the tricky situation in which you are. And we could now take an optimistic view and say that, what you would have liked here is that this be essentially imaginary. So, this is the good part of this is the good part of the substitution, and this is the bad part. When you took a point on the unit circle, you should have gone to a point on the imaginary axis. But This would have put you on a point in the imaginary axis, it is this which is creating a trouble here. So, the one thing is we want to do away with this term. Now, how do you do away with this term? You can't do away with this term, but by multiplying by its complex conjugate or dividing by the same term. So, it is clear that we cannot be happy with just a polynomial in Z or Z inverse. We need a rational, a proper rational function in Z or Z inverse to replace S, and that rational function in Z should be such that it cancels out this factor. That is the first observation. The second observation is that when omega goes from minus pi to plus pi, even if this term were to be absent, you would be taken only from minus 2 to plus 2 here, not from minus infinity to plus infinity. So, on that count also it is inadequate. In fact, this is the problem with any sinusoid or cosinusoid, as you might want to call it. Just a sine or a cosine term can never take you all over the real axis. Among the trigonometric functions, the sine and cosine functions do not take you all over the real axis. Which function takes you all over the real axis? The tangent function or the cotangent function. So, somehow we need a cotangent or a tangent function here. Now, how do we get a tangent function? You can't get a tangent function by subtracting z's. So, you can get a tangent function if you divide, that is another, you see, if you divide a sine function by a cosine function or a cosine function by a sine function, you get a tangent function. That is another reason why you would want some kind of proper rational function of Z to replace S. And in fact, if we take tangent, we have the answer. Tan omega by 2, when omega goes from minus pi to plus pi, tan omega by 2 would indeed run all the way from minus to plus infinity. So, if we can go from here, you see, we should try to get tan here, tan omega by 2 here. And how can we get a tan omega by 2? By dividing sin omega by 2 by cos omega by 2. So, let us do that. And in fact, once we allow for that division, we are also likely to do away with this trouble. So, we will be killing two birds with one stone in the proverbial sense, not literally. Indeed, to get tan omega by 2, what you are saying is you want j tan omega by 2, and j tan omega by 2 can be written as 2j sin omega by 2 by 2 cos omega by 2. And nothing stops you from multiplying by e raised to the power minus j omega by 2 in the numerator and the denominator. And in fact, there we have the answer. This is nothing but 1 minus e raised to the power minus j omega divided by 1 plus e raised to the power j omega. Please check that, so easy. And therefore, we have the answer to the transformation that we want. We are therefore asking for S equal to 1 minus Z inverse by 1 plus Z inverse. And now, let us check that this transformation indeed does all the jobs that we want it to do. Of course, one job we have already verified. Let us start with that thing that we have already done. So, let us start with Z equal to e raised to the power j omega. We will just, it is a formality, but we will just complete it. And we have seen that S becomes j tan omega by 2 here. So, the good thing is omega going from minus pi towards plus pi takes you from capital omega going all over from minus to plus infinity. Minus pi goes to minus infinity, 0 goes to 0, and plus pi goes to plus infinity. And this is monotonically increasing all that we wanted out of the mapping between the unit circle and the imaginary axis has been satisfied. Is that correct? As we move from minus pi to plus pi, there is also this mapping is 1 to 1. There is for every, you see, so I mean here you have j tan omega by 2. So, essentially what you are saying is omega, the capital omega is tan small omega by 2. That is the mapping that you are establishing here. And this is 1 to 1, that is the beauty of it. You know, for every small omega there is a unique capital omega, for every capital omega there is a unique small omega. In spite of the fact that small omega is on a finite interval and capital omega is on an infinite interval, we still have a 1 to 1 mapping. This is the beauty of this mapping. It is 1 to 1, it is on 2 both ways, so it is invertible, and of course it is monotonically increasing as we wanted it to be. Well, now about the left and the right half planes. So, let us write the inverse mapping, that is easier to deal with. So, we have S is 1 minus Z inverse by 1 plus Z inverse. So, of course, I can write 1 plus Z inverse times S is 1 minus Z inverse. So, I have S plus S Z inverse is 1 minus Z inverse, and that tells me that S plus 1 times Z inverse is 1 minus S. And therefore, Z is 1 plus S by 1 minus S. Now, we can say a lot about the real and imaginary parts. Let S be equal to sigma plus j omega. So, Z is of course obviously 1 plus sigma plus j omega divided by 1 minus sigma minus j omega. And therefore, we are interested in the magnitude of Z. It is the magnitude of Z that concerns us. So, let us see what happens to the magnitude of Z. The magnitude of Z is of course the magnitude of the numerator, which is 1 plus, in fact, let us take magnitude of Z squared. It is the square of the magnitude of the numerator, 1 plus sigma squared plus omega squared divided by the square of the magnitude of the denominator. That is easy to see. And of course, you have an omega squared common. So, the omega has no contribution to the magnitude. I mean, it does not affect the nature of the magnitude. What affects what makes the numerator and denominator different is the factors 1 plus omega squared and 1 minus omega squared. Indeed, when sigma is greater than 0, then 1 plus omega squared is bound to be greater than 1 minus omega squared. That is very easy to see. And nothing changes if you add omega squared to both sides. So, numerator is greater. So, numerator by denominator is greater than 1 clearly. Is that correct? For sigma greater than 0, sigma plus 1 the whole squared must be greater than sigma 1 minus sigma the whole squared. And in that case, the numerator is strictly greater than the denominator, and therefore, mod Z is more than 1. In contrast, when sigma is less than 0, then 1 plus sigma squared is strictly less than 1 minus sigma squared, and nothing changes if you add omega squared to both sides. and therefore, it is very clear that the numerator by the denominator is strictly less than 1, and therefore, mod z is less than 1. Is that correct? So, we have what we wanted. We have a satisfactory mapping of between the imaginary axis and the unit circle. The outside of the unit circle corresponds to the right half of the S plane, that is the real part of S being greater than 0, and the interior of the unit circle corresponds to the left half of the Z plane. There is a 1 to 1 there. In fact, it is not even too difficult to see that it is 1 to 1. You have a 1 to 1 mapping between S and Z, not just on the imaginary axis, but everywhere. You have got an inverse. So, you can go from S to Z or you can go from Z to S uniquely. So, we have luckily arrived at the transformation that we want. This transformation meets our requirements. S is 1 minus Z inverse by 1 plus Z inverse. Now, as a point for further reflection, I put the following question to you. How do you interpret this as an approximation of derivatives in terms of shifts? And the hint is to expand this in terms of a power series. Of course, you have a 1 minus Z inverse, but 1 by 1 plus Z inverse can be expanded as a power series, and that would give you some insight on what you mean, on what are we trying to do in terms of approximating derivatives by shifts. It is not too simple, but it is interesting. Of course, that is besides the main point of the discussion. We have got what we wanted, we are happy, we have got a rational function, the rational function does all that we want it to. Now, this transformation which we have now so satisfactorily constructed is called a bilinear transformation. It is called bilinear because it is a ratio of 2 degree 1 functions of the complex variable. This is an example of a bilinear transformation. The set of bilinear transformations has been studied in depth in complex analysis. In general, a bilinear transformation looks like this. Az plus b by Cz plus d equal to S is the general bilinear transformation, where A, B, C, D are complex constants in general. For those of you who wish to gain more insight into this transformation, I would recommend looking at any standard text on complex analysis, perhaps a first level engineering mathematics text. And in a reasonably comprehensive discussion on complex analysis, which is often a part of the syllabus of an engineering mathematics subject in the initial years, the bilinear transformation is described in depth. One of the important properties of a bilinear transformation is that it takes straight lines and circles to straight lines and circles. That is a property which is often pointed out in the context of bilinear transforms. And as you can see, this transform is no exception. It takes the straight line, the imaginary axis, into the unit circle, And of course, you can also think further to see what other straight line circle relationships there are in this bilinear transform. But that is typical of a bilinear transform. There is a straight line circle to straight line circle correspondence. Anyway, that was a remark to put you in perspective with complex analysis, but now we have the tools that we want, and we have agreed that we are going to use this bilinear transformation. So what we now need to do is to put down, what is the process that we will now follow? Now we shall take the discrete time filter specifications, discrete time filter specifications. Of course, these are unnormalized. Normally, you would be given unnormalized specifications. What are these unnormalized specifications? To take an example, suppose you have a low pass filter. You may say the sampling rate is so much, let us say it is 50 kilohertz, just to make a point. The pass band edge is 20 kilohertz, let us say. The stop band edge is 30 kilohertz. Can it be? No, it can't. So this can't be. Let us make it 22 kilohertz. If the sampling rate is 50 kilohertz, at best we can deal with a frequency of 25 kilohertz. So stop band edge is 22 kilohertz, and the tolerances of the pass band and stop band are 0.1. So what we are saying in effect is that we want this kind of a frequency response. Of course, I am showing only the positive side. Now you see pi corresponds to 25 kilohertz, since the sampling rate is 50 kilohertz, and therefore 20 kilohertz would essentially be 4 by 5 times pi, or 0.8 times pi. This is the pass band edge. And 22 kilohertz is 22 divided by 25, that is 0.88 pi. And therefore, you have a stop band going from 0.88 to pi, and a pass band going all the way from 0 to 0.8. And of course, you are allowing the response to vary between 1.1 and 0.9 here, and from 0 to 0.1 there. This is the response that you want to realize. So this is how you would translate the specifications into the normalized angular frequency domain. Or these are called the normalized specifications on the normalized angular frequency axis. Is that clear? Is that clear how we go from the unnormalized specifications to the normalized specifications? It's very easy. All that we are doing is really to normalize the frequency axis. Is that correct? So here the changes, see, it's very interesting. The S to Z transformation, this process of normalization, are all transformations of the independent variable, not the dependent variable. The dependent variable is not being transformed. It's the independent variable which is being transformed. And the dependent variable is being carried with the independent variable. Is that right? Now, once we have the normalized specifications, the next step. So, remember, this can be similarly done for band pass, similarly for high pass filter, band stop filter. You can go to a set of normalized specifications. And the next thing to do is to use the bilinear transform. The bilinear transform will take you from the normalized discrete specifications to analog specifications. That means you have specifications in omega, and now you have here specifications in capital omega. And how would we carry out this movement from discrete small omega to capital omega? Capital omega is tan omega by 2. That takes you from omega to capital omega. So, the nature of the, so here we now have a corresponding analog filter to be designed. So, what would you do next? Of course, you would design that analog filter, take advantage of the known methods for analog filter design and design that analog filter. So, we will assume we design that analog filter. Let us call it H analog, and that would be a function of S. It is a rational function of S, rational, stable, causal. There are several different approaches, and we will look at some of them. In fact, we will begin by looking at the low pass filter design. So, once we have an analog filter, we are done, because now all that you need to do is to replace S by 1 minus Z inverse by 1 plus Z inverse to get a stable, causal, rational, discrete filter. And our job is done. So, this is the scheme of things. Therefore, now in the next lecture, we need to look at how we can design analog filters. Given the specifications of the analog filter, we will begin with a low pass analog filter as a case in point.